All right, everyone, and welcome back to the AI Research Roundup. I am Alex. Today, from the Papers with Code trending list, we're looking at Dolphin document image parsing via heterogeneous anchor prompting, a fresh paper from May 20th, 2025. So it's all about document image parsing. That's teaching AI to understand complex documents with text, figures, and tables. Current ways of doing this can be slow or struggle with layout. Dolphin uses a neat two-stage analyze-then-parse approach. First, it finds different layout parts, or heterogeneous elements, which act as anchors. Then, using these anchors in specific instructions called task-specific prompts, it processes all these parts in parallel. This makes it faster and more accurate. Dolphin is also a multimodal model, meaning it gets both the visual layout and the text. This multimodal capability, where Dolphin processes both the visual layout and the text, is a key part of its design. And if you're interested in exploring Dolphin more deeply, or even trying it out, the authors have made the code for this work publicly available. The official repository contains the demo code, the pre-trained models for Dolphin, and also clear instructions for installation and for running inference. That's the process of using the trained model to analyze new documents. So it's all there if you want to dive in. Okay, so speaking of performance, figure 1 here gives us a nice visual comparison. It's a radar chart showing how Dolphin, represented by the red line, stacks up against other advanced vision language models. The further out a line is on any axis, the better the performance. We can see various benchmarks, like page-level parsing measured by edit distance, or ED, which is a way to quantify how different the model's output is from the correct text. Lower is better here. For formulas, they use the character difference metric, or CDM, and for tables, it's the tree edit distance-based similarity, or TEDS, both where higher scores are better. And then there's frames per second, or FPS for speed. Dolphin pretty clearly covers the largest area, showing superior performance in most of these. So that radar chart gave us the what in terms of performance. Now, figure 2 here gives us a look at the how. It details Dolphin's two-stage document image parsing system. First, in stage 1, which is page-level layout analysis, Dolphin takes the input document image. It uses a layout analysis prompt to identify and output layout element groups in a structured format, like JSON. Basically, these are the different components like figures, captions, tables, and paragraphs, each with its location marked by a bounding box and arranged in reading order. These elements then act as anchors for the next stage. Then, stage 2 is element-level content parsing. This stage takes those identified elements and processes them in parallel, which is key for speed. As shown on the right, it uses specific prompts for different content types, like p_table to parse tables into HTML, or p_paragraph for text and formulas, outputting latex for formulas. The system uses a Swin transformer, which is an advanced vision model architecture that acts as the visual encoder to understand the image. Then, a decoder component, employing cross-attention, a mechanism that allows the model to selectively focus on relevant image regions when generating the output, translates these visual features into the final structured text, like HTML or latex. Okay, so figure 2 showed us the how of Dolphin's two-stage system. Now, figure 3 here, it visualizes the results of that process. We see 3 example documents presented, an English one with formulas, another English document with a table, and a Chinese text document. For each of these examples, the left column shows the stage 1 output, which is the identified layout elements and their reading order. Then, the middle column displays the element-specific content that's been parsed in stage 2. And finally, the right column presents the complete document, rendered in Markdown format. This really helps to see the system's practical output on different types of pages. Right, so where figure 3 gave us that end-to-end view of rendered documents, figure 4 here zooms in a bit more, demonstrating Dolphin's specific element-level parsing capabilities. We see input image snippets in the top row, and then directly below in the bottom row are the corresponding recognition results. On the left, it shows how Dolphin handles text paragraph parsing in complex layouts. The middle example highlights its bilingual text recognition abilities. And on the right, we see an example of complex table parsing with the rendered results shown. This gives us a clearer look at its fine-grained parsing accuracy. Alright, so After seeing those specific element parsing examples in Figure 4, Figure 6 here provides a really clear case study. It focuses on the effectiveness of using type-specific prompts, which we talked about as part of Stage 2. On the left, you see an input table image. Below that, when a generic prompt is used, the system actually misidentifies the table as a formula and outputs latex code. But then, on the bottom right, when a type-specific prompt for tables is used, Dolphin correctly parses it as an HTML table and renders it successfully. This really underscores why those tailored prompts are so important for accuracy. That example with the table really drives home the cleverness of Dolphin's approach, particularly with those type-specific prompts. Overall, Dolphin presents a really robust two-stage system for parsing complex documents, making information much more accessible from images. This kind of work is crucial for unlocking the vast amounts of data trapped in visual formats. Well, that's all for this AI Research Roundup. Thanks for tuning in. I'm Alex.